All right, we're ready to start. Um, yeah, I think let's get going. So, still talking about probability. I was looking at your guys' current homework assignment, which when does it due? I don't know. It doesn't really matter, I guess, but it's due at some point. I guess on the 8th. So Monday, right? Yeah, Monday. Anyway, um, I was noticing it doesn't seem to have what I would consider to be a standard kind of Bayes formula question, which is a little surprising to me. Um, I still think we should talk about it. I can't imagine it not showing up on your final. So apologies if it doesn't show up on your final, but my gut is that you're going to see a question in this vein on your finals. So, and even if you're not, still worth talking about. So let's go ahead and start with this, and then we'll kind of see where to go after that. So here's the setup, and it's kind of lengthy here. Um, a rare disease affects 1 out of 1,000 people. Although, I mean, that doesn't seem that rare to me personally, right? It's still like 8 million people in the world if it's 1 out of every 1,000, but whatever. Um, a blood test correctly detects the disease 99% of the time, but also gives a positive result in 2% of the cases when the person does not have the disease, also known as a false positive disease. Um, so the first thing I want you to actually do is so actually let's name the events and then I want you to kind of write down the things that we know. So let's say that A is the event of having the disease. A complement obviously is not having the disease. And B is the event of having a positive test. And then B complement would have be a negative test. So there are three numbers on this question so far. The numbers 1 out of 1,000 or 0.001, 99% or 0.99, and 2% or 0.02. You should be able to write down what probabilities each of those numbers corresponds to, whether it's a straight probability or a conditional probability. So there are three things you should be able to write. Some probability equals 1 out of 1,000. Some probability equals 0.99, and some probability equals 0.02. Start with that. Okay, let's take a look here. So the problem tells us that a rare disease affects 1 out of every 1,000 people. So the probability of having the disease is 1 out of 1,000. Straight direction, straight probability, right? So the probability of event A is 1 out of 1,000. After that, they say a blood test correctly detects the disease 99% of the time. So that's not the probability that we're getting a positive test. It's knowing that someone has the disease, the probability of having a positive test is 99%. That's a conditional probability. So we're going to say that the probability of a positive test given that the person has the disease is 0.99. And similarly, point we also get a positive test 2% of the cases when the person does not have the disease. So given that they don't have the disease, a complement, the probability of a positive test is 0.02. So the probability of B given a complement is 0.02. Cool. So it's definitely important when you read a question like this to be able to write down the probabilities using whatever event names you want. So then first question here, and we did one like this last time. Find the probability that a random person tests positive. And there's two ways to think about this. And I'm going to kind of show you the formulaic way first because I think it's good to know, but I also really want to do it the other way because I think it's better. So we're trying to find the probability of a positive test. So we're finding the probability of B. So one way to think about this is using what's called the law of total probability. So if you test positive, you either also have the disease or also don't have the disease. Those are literally the only options. You can draw a Venn diagram if you like. You can say like, here's the very, very small portion of people that have the disease. Here's the rest of them that don't have the disease. And then in this overlapping circle, here's the people that are testing positive. So if I'm testing positive, I'm either testing positive and have the disease over here or testing positive and don't have the disease over here. And that's it. That is everyone who's testing positive. So the law of total probability tells us that's going to be the probability of B intersect A plus the probability of B intersect A complement. Right? If you're in B, you're either also in A or also in A complement, and nothing else is possible. At least in problems like this where A and A complement kind of make up everybody, right? Everyone in the world either has this disease or they don't. Yeah. The law of total probability. So yeah. So this is an example of the law of total probability. Probability. And technically you can have more pieces to it. So like if it was something else where like everyone in the world was divided into three categories, I can't think of like what three good categories would be for everyone in the world. But let's say there were, then you could either test positive and have the first attribute or the second attribute or the third attribute. And all three of those intersections would add up to all the probability of having a positive test. Okay. So then we still don't know either of these things though. So how do we write them? Well, we do know how to calculate the probability of an intersection. The probability of B intersect A is equal to the probability that A happens multiplied by the probability of B given that A happens. I don't love this formula, or I don't love this version of this formula. The version of this formula that I really actually am thinking of in my head when I write this down is this one. I'm thinking of the fact that the conditional probability B given A is equal to the probability of B intersect A divided by the probability of A. So really what I'm doing is I'm taking this equation and then manipulating it to look like that. Oh, look, yeah. B intersect A is just probability of A multiplied by the probability of B given A. And similarly, the probability of B intersect A complement is just the probability of A complement times the probability of B given A complement. And looking up here, we can see that we have all of those things except for one of them that isn't written down, but we actually do know it. If you know the probability of having the disease is 1 out of 1,000, the probability of not having it is 999 out of 1,000. So we have all the information we need to find the probability of B here. So the probability of B is equal to, I'm going to write these formulas again. Yeah, sure. Probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement, which is equal to, let's see, it's 0.001, that's 1/1000th, times 0.99 plus 0.999 times 0.02. And that ends up being about 0.02097. So just slightly higher than 2%. Which again, if we think about what's going on here, makes some sense. If 2% of the population, or I should say, if almost the entire population doesn't have the disease, and you're going to get 2% of those people testing positive, that's making up the majority of your positive tests. The other positive tests that are actually the ones who have the disease are making up a very small part of that, which is kind of interesting. There's something else I want to say here. Oh, I know what it was. There's another way to think about this, though. So even though this is totally fine, I don't think it's the easiest way to approach this problem. I think it's much nicer to draw a tree diagram. So in the tree diagram, the first branch of the tree should be the thing that is kind of the given thing in your conditional probability. So in our conditional probabilities, we have the probability of B given A, meaning the A thing should happen first and the B thing should happen after it. So my first branch in my tree is either A or A complement. And the nice thing about these tree diagrams is that in each branching, every branching should add up to 100% or 1. So, right, you either have the disease or you don't. Well, the probability of having it is 0.001. The probability of not having it is 0.999. And then if you have the disease, well, you can either test positive or test negative. But it's not just the probability of B or the probability of B complement. It's really, this is really B given A. And this is really B complement given A. So the probability of testing positive, given that it already happened, was, well, we said it was 99%. Meaning the probability of testing negative, given that you have the test, a false negative would be 1%. Similarly down here, B given A complement or B complement given A complement, right? We have, well, the probability of a positive test given not having the disease, we said was 2% or 0.02. And the probability of not testing positive has to be everything else, so 0.98. I should say the probability of not testing positive given that you don't have the disease. And here's the part I really like about this. To find the probability we were asking for, you just have to find all of the pathways that end at the thing we're trying to get to. So if we're trying to find the probability of B, it's just going to be all the ways you get to B. So it's either A and B or not A and B. That's it. So it's going to be 0.001 times 0.99. That's A and B. Or plus 0.999 times 0.02. Not A and B. Same numbers, same calculation, just a different kind of perspective on how we're getting there. Either way is fine to think of it. I just think this is nice. Questions about this so far? Yeah. Ooh, that's a good question.
This one random person.
No, so we can use, I mean, there's other like examples that also are nice to use this diagram for, but it is often used in these situations where you have like conditional probabilities, where you're talking about the probability of something happening given that something else has already happened. So I'd say they're useful when you have a conditional probability kind of situation. All right. So now the much more interesting question to answer is what is the probability of actually having the disease given that you have tested positive? So the first thing you want to do is write down the probability that the conditional probability that we're trying to find. Well, it's not one of the ones we're already given, right? It's not B given A because we know the probability of a te positive test given that you have the disease is 0.99. We're trying to find the probability of A given B having the disease given a positive test, right? Because that's actually what matters, right? If you test positive for this thing, you want to know how likely is it that they actually have this disease, this affliction. Well, let's see here. So whenever I see this kind of question, almost anytime I'm trying to find a conditional probability, my first thing I jump to is always writing it as the quotient, as writing it as the probability of A intersection B divided by the probability of the given thing. Now, unlike when we were doing conditional probabilities with all those cards, this is a situation where we can't really like talk about the reduced sample space. Like where we talk about like kings and sevens, like, oh, we're just looking at the sevens, fine. Here we can't really do that. We really kind of have to use the formulas here. So again, this is where I'd say the tree is super useful. So looking at the tree, it's actually really, really nice if we think about what we want. So on top, I want A and B. Cool. There's one way to get there. First A, then B. So on top, it's going to be 0.001 times 0.99. I have no idea why sometimes I write zero in front of a decimal and sometimes I don't. I just do. Like it's like here it feels like it's good to. Here, I don't know. That's I'm just looking at like why do I sometimes write zero? Who knows? Anyway, not important. On the bottom, the thing we just calculated, or alternatively, thinking about it, all the pathways that get us to B. So it's the pathway that goes through A. So here's A and B, 0.001 times 0.99 again. I'll point out that when you do this, you always get the same thing on the bottom that you already had on the top, plus the other pathway that gets us to B, A complement and then B, 0.999 times 0.02. Or writing it out. Well, actually, we'll talk about the numbers, then we'll write the formula. So this is going to be what we get about, well, yeah, those numbers are approximately 0.047. Or in other words, about 4.7%. So this is the point of this question is really to kind of combat some thinking that people usually have, which is that if someone told you that the test, I forget the words. There's two words we talk about testing, like I really don't know them actually at all. Like there's two words about like whether like how accurate the test is, and then like some other word. Anyway, this test, right? If you have the disease, it's positive 98% of the time, which leads people to kind of misconstrue information, right? People often think, oh, well, if the test is positive 98% of the time that someone has the disease and I tested positive, that would mean there's a 98% chance. No, no, not at all. It's much more dependent on the prevalence of the disease. So here we see that a person testing positive has only a 4.7% chance of having the disease, not a 98% chance of having this disease. So it's a really kind of interesting that this reverse conditional probability is a much, much, much different value. Kind of neat. There's something else I want to say. Oh, so I would personally, I would always attack. So actually, this is an example of Bayes formula or Bayes rule, whatever it's called. Um, I would honestly just do it this way every time, but there is a formula which is really just writing out what each of these things are. So here's Bayes formula if you really want it spelled out. Bayes formula. And I always think of it as the formula for reversing the conditional probability. So essentially you're given you know the probability of A given B and you're trying to find the probability of B given A, essentially. So or vice versa, whichever way. So we have the probability of A given B is equal to this, which is then equal to the probability of B given A times the probability of A over the probability. I kind of wrote those out of order. I don't love that I did that. Oh well, it doesn't really matter. Probability of A times the probability of B given A plus the probability of a complement times the probability of B given a complement. That is Bayes' formula. Which I guess I could say I've memorized at this point, but only because I've done it so many times. I don't memorize this. I remember this tree thing. And then this formula eventually just comes out because you've done it 1,000 times. Okay. Here's a question that always feels weird to me to ask, but we should ask it because it's worthwhile. Because if you tested positive once, you'd be like, well, maybe I have this disease. So maybe I should test again, right? Because there's really not a super high chance of having the disease given one positive test. So really, we're going to answer the better question, which is, well, first we'll answer the intermediate question so we can get to the better question. Question C, what is the probability that the same person tests positive twice? So this always feels odd to me, and I don't know if I really love the way I've done this, but I'm going to show it anyway because it's just, yeah. Here we should make an assumption that we'll talk about how valid it is. So we're going to assume that the test results are independent, right? We're not considering the first test result has, we're just doing a second test for everyone, not based upon the fact of whether or not we know they had the disease. Okay. So then we're asking essentially, what's the probability of getting two positive test results? Well, again, it's really going to be the same kind of breakdown. We're going to say on our tree, you can either have the disease or not. Same probabilities as before. Probability of having the disease is 0.001, not having it's 0.999. If you have the disease, what's the probability of two positive tests given that you have the disease? Well, since the tests are independent, you're just going to get to multiply those probabilities together, right? The probability of the first test is positive is 0.98. Or wait, 0.98 or 0.99? Sorry, 0.99, sorry. The probability of the second test is positive is also 0.99 because we're saying that they're independent. And when events are independent, right? In fact, yeah, we talked about this briefly. Right, when things are independent, one of the ways or one of the things we know is true is that the probability of their intersection that both happen is the same as the probability that each happens multiplied together. So two positive tests just mean it's going to be 0.98 times 0.98. Given that someone has the disease. And similarly, if they don't have the disease, the probability of two positive tests, given that they do not have the disease, is going to be, well, the probability of getting two false positives. So 0.02 times, I wrote 0.98 even though I said 0.99. Sorry. The problem is I'm looking at that 0.02 and thinking it should be the rest, and that's not true. 0.02 times 0.02. So let's see. So doing the math, we get the probability of two positive tests is going to be 0.001 times 0.99 squared plus 0.999 times 0.02 squared, which is going to be approximately 0.00138. So barely a tenth of a percent of a chance of getting two positive tests for just any random person we select. If you knew the person had the disease, very high chance of getting two positive tests, right? 98% times 98% is something like on 95% still. If the person didn't have, it'd be really hard to have a two positive test if you didn't have the disease, right? 2% of 2% is very, very small. Okay, but now the question we really want to answer, which is, I bet you can guess what it is. What's the probability that the person actually has the disease given that they have these two positive tests? So if the person tests positive twice, what is the probability that they have the disease? So really, it's kind of the same thing we did before. In fact, this is why we did this part here, so that we don't have to kind of work through all kind of the gross part of it. Here's what we're looking for. The probability of having the disease given two positive tests. Well, typical formula, it's the intersection. It's the probability of having the disease and having two positive tests, or the intersection of having the disease and two positive tests, divided by the probability of having two positive tests. We can write more formula if you want. I don't know if we need to personally, but we will. So the top part we already know, but I'll just remind you, it's really just the usual law of total probability thing, right? It's the probability of having two positive tests and having the disease, plus the probability of having two positive tests and not having the disease. On top, the probability of having the disease and two positive tests is just the probability of having the disease multiplied by the probability of two positive tests given that you have the disease. To me, this one's always the hardest part to remember, that this intersection becomes a probability times a conditional probability. To me, that one always feels like I have to actually think about what's going on. Okay, yeah. And it's having the disease and then two positive tests given that we have the disease. Question. Mm-hmm. Sure. I'm not. Is it on his canvas? Let me take a look real quick. Under the what? Okay, let me see here. Sorry, I thought I had it up. Tim, where are you at? Tim, there you are. Module, is it like at the bottom?
Yeah.
Okay. Midterm two, final exam, formula sheet. Okay. Oh, good. And he's got lots of practice tests for you. How great. That's nice. Self-design. Oh, wait, self-design practice tests. That doesn't sound like it's actual. Okay. It really is though. Like it is well intended and is a good thing to do. Like to think about what questions might be on the final. All right, let's see here. You said the formula looks a bit different. Where are we at? Let's see. It's a lot of formulas. Sure. So yes. Well, so he's got the letters backwards from how I have them, right? But that doesn't matter, right? But so I would just say he's not writing out the bottom part, right? So I would point out, right, like here's so really what his version is compared to my version, his version is this numerator and this denominator, which is fine. So let me give me a second here. So here's what I would say. Here's the version. Here's what we're starting with, right? This. And then I'm writing it like this, obviously, as one would typically, right? And again, whenever you're finding conditional probability, that is where you should start, I think. It doesn't matter which order you write the intersection, right? A intersect B, same as B intersect A. And then here's the step that he's taking. He's just simplifying the top and saying, oh, we can rewrite the top as the probability of A times the probability of B, apologies, times the probability of A given B. And he's not changing the bottom, which is fine. But that's not, in my opinion, that's not how like the expanded formula is usually written out. It's a good starting place, but then we have to know how to find the probability of A. So here's what you've got on your formula sheet. And here's where I would go further. This is going to be equal to the probability of B times the probability of A given B. And then I've written it in the opposite order on top. That's fine. Order of multiplication doesn't matter. Divided by the probability of A, I'm really going to write as the probability of A and B plus the probability of A and B complement. Law of total probability. And then I would even take it one step further, say the top is still the top. Ah, darn it. The top is still the top. That means you have to write it the same way you wrote it before. And the denominator, well, I'll point out that right there, that's the same as that, which is just your numerator. That's why I said the thing about how your numerator is always showing up again in your as part of your denominator for Bayes' rule, always. So you're going to get the probability of, let's write it the right way, B times the probability of A given B plus, and then this one's going to be the same thing except using B complement instead of B. So it's the probability of B complement times the probability of A given B complement. So in my opinion, this is what we usually think of as Bayes' formula. He's just writing a less extended out version of it. Okay, so can we finish this up? No, we didn't finish this quite yet. So we're almost done with this. So let's just finish this off real quick here. So let's see. We have the probability of A, which is, I forget what it was, 0.001. And then the probability of two positive tests given A is 0.99 squared. And I'm just going to be smart here and say, okay, I know that the numerator shows up again in the denominator. So it's again going to be 0.001 times 0.99 squared plus this, which is really just these two parts of the path on the tree diagram. It's the probability of A complement, 0.999, times the probability of two positive tests given that you had not had the disease, which is 0.02 squared. If you're taking a test, you should leave your answer like that. There's no, unless you get to use a calculator, which I don't imagine you do. Do you? Oh, really? Okay. Well, then you probably should simplify this. Okay, then you should leave it like this. Yeah, definitely like this. Like I don't think anyone cares if you're able to input things into a calculator. I mean, you should be able to input the things correctly into a calculator, but like no one's like that's not like a skill we really test, right? It's just like you can do it or you can't. So let's see. Here we end up getting. Sorry, I just lost my spot here. I'm on the wrong page. I'm like, what is this? Wrong one. There we go. We get about 0.71. So a much, much higher probability of actually having the disease if you had two positive tests, which makes sense, right? It's a really, really hard to have two positive tests if you don't have the disease. Cool. It's kind of a cool question. All right, let's see. What time is it? 12:47. Okay. Let's look at a few more examples. Oh yeah. Yeah, we should talk about this. Okay, cool. Yeah. All right. Oh, there was something else I was gonna say. Two things. Where'd they go? Yeah, here we go. So why is my font so small? I don't love that. Let's get bigger. There we go. Much bigger. Okay, cool. Yeah, that's maybe too big. Okay. smaller. So just want to mention two things on our canvas. I did just post a practice final. I can't attest to how similar or apt it will be for the final he will give you. I wrote it a couple quarters ago for someone else's class. It's still, I mean, the questions are still from 17C, so it's probably good practice. There's also solutions there. And then the other thing was there is a survey about this class that I would appreciate you all filling out when you have a moment. It probably takes 5 minutes. It is anonymous, or at least I think it's anonymous, but either way, I won't know who fills out what. My supervisor might see names, but I will never know names. So feel free to write whatever you want. I would appreciate any feedback you have about like how to make the class better. But really, it's kind of one of the few ways I actually get evaluated. So please do fill it out because it's kind of all my supervisor has. Like in April when we do our performance evaluations, it's like, well, these are what the students said. I'm like, great. So anyway, please fill it out when you have a chance. It doesn't take that long. Um, yeah, I think that's all I had. Okay, cool. There's nothing else on there? Right. Now I'm like, make sure there's nothing else on there that I want to say. No, just useful stuff. Yeah, okay. Sorry, sometimes I throw things on. Oh, I know what it was. And then about my office hours next week. In case you were looking for, what day's your final on? Thursday. Okay, so plenty of time before to study. I did post an announcement, I think. It kind of got, yeah, oh yeah, that's right, because I was canceling my office hours on Tuesday. And then finals week, my office hours are all in the library down in the drop-in with the AATC. And it's Monday through Wednesday, 11 to noon and 1 to 3, Thursday, 11 to noon and 1 to 2. So if you're looking for me or some of the other math specialists, that's where we'll all be. Cool. All right, back to this. So where'd my examples go? Yes, there. So I always find this next question kind of weird, but there is definitely one like it on your homework. So you draw two cards from a deck without replacement, which makes sense, right? If someone's talking about drawing cards from the deck and they don't specify, you should assume you're not replacing the cards because that's usually how cards get drawn from a deck of 52, standard stuff. Here's the question that I always think is weird. Find the probability that the first card was an ace, or whatever we're talking about, given that the second card was an ace. I can spell ace. Okay. And to me, this feels weird because like you draw the first card. Essentially, you draw the first card, you don't look at it, and then you draw the second card, like, oh, I got an ace. What's the chances that the first card was also an ace? Okay, so let's do the math. So let's write down our events. Let's say A is the event that the first card is an ace. B is the event that the second card is an ace. So we want to find the probability of A given B. The probability of the first card is an ace given that the second card is an ace. Interesting. So again, we know a few things. Well, we know we should be reversing the probabilities here because, well, actually, I don't feel like that's a true statement. So yeah, I'm trying to think about what I really want to say here. Well, let's talk about what we do know. In general, the probability that the first card is an ace, just without any conditional probability, should be 4 out of 52. Right? The top card of the deck is an ace is, well, there's 4 aces and there's 52 cards in the deck, so 4 out of 52. Now, the problem here is that the probability that the second card is an ace, you can't just say it's, well, what out of 51? Is it 3 out of 51 or is it 4 out of 51? It depends on whether or not the first card was an ace. So, what's the probability of B? Well, you can either have first event A happens or it doesn't, but you draw the first card. And the probability of drawing an ace is 4 out of 52. And the probability of not drawing an ace is 48 out of 52. And yes, I realize we could reduce these fractions, but I do kind of feel like it's smarter not to because it's just good to think about the number of cards out of the number of cards. Okay, then either the second card is an ace or it's not. So if the first card was an ace, the probability the second card is an ace is 3 aces left out of 51 cards in the deck. And the probability the second card is not an ace is 48 not aces left out of 51 cards in the deck. Notice again, like I said before, each of my branches is still adding up to 1, right? 4 out of 52 plus 48 out of 52 is 1. 3 out of 51 plus 48 out of 51 is 1. Here, because again, it's really just you're counting all the things that can happen. It's either this or that, and nothing else is possible. Down here, if you didn't draw an ace first, then the probability of the second card is an ace is 4 out of 51. And the probability of the second card is not an ace is 47 out of 51. Right here, we didn't draw an ace first, so there were still 4 aces left in the deck. We drew some other card that wasn't an ace. There's 4 aces left in the deck. There's 47 cards that aren't aces left in the deck. So the probability of B is equal to the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement, which ends up being, let's see, 4 out of 52 times 3 out of 51 plus 48 out of 52 times 4 out of 51. I feel like I'm making a mistake here. Let me double check. No, that's right. And if you simplify these, look what happens. Do I really want to look what happens? Sure. So I get, I'm trying to think about how much I should simplify this here. 4 times 3 is 12. No, let's be smarter about this, James. So look at this, look at these fractions. From the numerator, well, both the denominators are the same. So it's out of 52 times 51. And in the numerator, I can factor out a 4. So I've got 4 times 3 plus 48. 3 plus 48 is 51. 51's cancel. And you get 4 out of 52, which is 1 out of 13. So essentially, we didn't need to think about it at all. Right? If you had kind of ignored the fact that we drew a card completely, since we don't know what happened with that card, the probability that the second card is an ace is just the same as the probability that the first card in the deck is an ace. 4 out of 52. If you don't know what happened with the first card, it's kind of like it never happened. Interesting. Kind of weird. Right? So here's what I'm telling you essentially. I took the deck, I put the first card face down over there. And then the probability that the next card is an ace is 4 out of 52. Right? If I don't know what that card is, it doesn't matter if it's sitting over there or over here or on the bottom of the deck, right? I can put it anywhere. The probability that the second card is an ace, if I don't know anything else, is still 4 out of 52. It's kind of interesting. So then to answer the question, right, because we're not done, we haven't answered the question yet, we're trying to find this probability. So that's the probability of A and B divided by the probability of B. But we know the probability of B is 1 out of 13, or 4 out of 52. And the probability of A and B, well, here's the path that gets you to A and B. It's 4 out of 52 times 3 out of 51. The 4 out of 52s cancel, and you end up getting just 3 out of 51, which is 1 out of 17. So the probability that the first card was an ace, given that you know the second card is an ace, is the same as the reverse. Right? If I told you the first card, it's much easier to answer the other way. If I told you the first card was an ace, how many aces are left in the deck? How many cards are left in the deck? There you go. Sorry, that's why you don't reduce fractions. It's equal to 3 out of 51. So the order you pick the cards in doesn't actually matter if you don't know things, right? The probability that the second card was an ace given that oh my gosh, I'm saying it the wrong way. The probability that the first card was an ace given the second card was an ace is the same as the probability the second card is an ace given the first card was an ace. Because you're assuming you don't know the thing about the other thing. Kind of neat. It kind of is like, that doesn't seem like it should work that way, but it totally does. Okay, how much time? Sure, yeah, we should do that too. So we briefly talked about independence, like very briefly. So I'll remind you because I do think it's something that's probably going to come up somewhere. It's usually something that comes up. So here's a reminder about what it means to be independent. So independence. We say that A and B are independent events if all of the following are true. And really, when we say all the following are true, means if one of them is true, all of them are true. So either one, the probability of A given B is equal to the probability of A, or two, the probability of B given A is equal to the probability of B, or three, the probability of A intersect B is the probability of A times the probability of B. All three of these things are the same, just different versions of the same formula. The way I think about it is if this is true, right? So from this one here, if you rewrite this, well, we know the probability of A given B, the formula for that is really the probability of A intersect B divided by the probability of B. But then if we're saying that's equal to the probability of A, then you can see how we get to this formula over here by just multiplying both sides by the probability of B, right? Taking this part of it and doing that. And the same thing for this one. It's just this just the reverse. Um, I will also point out this is very, very not the same as two events being mutually exclusive or disjoint. So just as a reminder, sure, disjoint. A and B are disjoint or mutually exclusive if the probability of A intersect B is equal to zero. Or in other words, the intersection of A and B is empty. There is one case where this is not true, where they actually are not. Well, so here's what I actually usually like to say. Being independent and being mutually exclusive are mutually exclusive. You can be one or the other, but not both, with one exception. If you have two events and the probability of one of them is zero, then the events can be both mutually exclusive and independent. But it's dumb to talk about an event where the probability is zero. So that's why it's not usually talked about. Right. But here's how you can think about this, right? If two events are mutually exclusive, let's say the two events are mutually exclusive, and I told you that one of them happened. Well, then you know the probability the other one happened. If one of them happened and their overlap is empty, that means the probability of the other one happening is zero. So knowing that one of them has happened has affected the probability of the other one, which means they're not independent. Unless, of course, the probability of the other one was zero. But we're not looking at that case. And in fact, there's a homework problem about that that specifically specifies that the probabilities are positive, meaning they are not zero. So that's what we're talking about there. So try to keep them separate from each other. Try to keep them disjoint from each other. All right. So how much more do we have to say here? Sure. Yeah, I'm just trying to think about, sure, let's look at this example and then we'll see how much we want to do. Oh, I forgot to pass out the attendance form. I forgot, I just hadn't gotten to it yet. So yeah, let's look at this one and then sure. So sure, problem, whatever number this is, three, I think. Sure. A jar contains some marbles. Back to the marbles. Contains four red marbles and six green marbles. You pick two marbles, one at a time, meaning we were thinking about which one comes out first, which one comes out second, without replacements. Find the probability that the second marble is red. And I'm going to let you guys do this one. I think I will point out it's very, very similar to how we just did that card one, where especially finding the probability, the part where we drew the tree diagram, where we find the probability that the second card was an ace. So I would say, let's say that I'll help you out a little bit. Let's say that R is the event of a red marble and W is the event of a white marble. You're trying to find the probability that the second marble is red. So make your tree diagram. Your first branch, one of two things can happen. And then your second branch, one of two things can happen. Did I mean green? Yeah, I did. Sorry. I think I saw a red and white marble question earlier somewhere else today. Yeah, sorry. Let's say that G is for green marbles instead of W is for white marbles. Thank you. Good call. It's Christmas, right? Green and red. Yeah. And I'll admit, I don't know if this tree diagram is specifically necessary here, but I like it anyway. So here's what we've got. On your first pick, there's a 4 out of 10 chance of getting a red one, 6 out of 10 chance of getting a green one. If your first one was red, then on your second pick, there's a 3 out of 9 chance of getting a red one and a 6 out of 9 chance of getting a green one. If your first pick was green, then on your second pick, there's a 4 out of 9 chance of getting a red one and a 5 out of 9 chance of getting a green one. So the probability that the second one is red, wow, I keep writing an R when I mean to write a P. Probably the second is red. Well, it's all the ways you can get the second one being red. So it's either going to be a red one first times a red one second, or a green one first times a red one second. Which I feel like you probably could have reasoned out without doing the dream, right? You could have said, okay, well, it's either going to be red, red, or green, red. And the probability of red, red is 4/10 times 3/9, and the probability of green, red is 6/10 times 5/9. So maybe not super necessary here, but still doesn't hurt. Let's see, calculating this, we get 12 plus 24 is 36 out of 90, which reduces to what? Is that right? 12 plus 24, yeah, 36 out of 90, which reduces to, let's see, 4 out of 10, which is 2 out of 5. Again, I'll point out we're seeing the same kind of thing we saw with the cards. That if you're just asking about the second thing and you're not caring about what happened to the first thing, it's kind of like you're asking what's the probability that the first marble is red. Oh, it's 4 out of 10, which is 2 out of 5. Kind of this still kind of weirds me out sometimes. Like, oh yeah, right. If I just like toss away the first marble and don't look at it, the probability that the second one is red is just like if it'd been the probability the first one I picked was red. Yeah, I mean, as you can clearly see, this still kind of is like, oh yeah, that's kind of weird that it works that way. Yeah, question. Yes, well, I don't say time. Actually, I'm not sure what you mean. Say what you mean, actually. No, dude, because I'm not sure if I'm understanding you correctly. Yes, thank you. Okay, that's what. Yes, so right, this is exactly the probability that the first one is red times the probability that the second one is red, given that the first one is red, plus the probability that the first is green times the probability that the second one is red, given that the first one is green. Exactly. Yeah. And then the question that we really want to answer by doing all this is, are the events picking a red marble first and picking a red marble second independent? And this is where things are a little bit weird. So, how do we check for independence again? Well, there's 3 different formulas you can think about. I'm thinking, which one am I actually thinking about? I don't even know, to be really honest. Um, I'm probably thinking about this one where I'm saying, okay, well, I want to know essentially, does picking a red marble first affect the probability of picking a red, oh my gosh, words, a red marble second. Let's think about this before we actually write down the math. If you picked a red marble first, is that going to affect the probability of picking a red marble second? It seems like it should, right? If I've got one of the marbles out, then it seems like it should change the probability of getting a red marble second. Well, let's actually do the math now. So here's the way I'm thinking about this. I'm asking the question, does picking a red marble first affect the probability of picking a red marble second? So essentially, does picking a red marble second, given that you picked a red marble first, is that equal to the probability of picking a red marble second? That's what we're actually asking, right? Is this conditional probability where you know you picked the red marble first different than without it? Well, let's see here. We know this one, the probability of picking a red marble second was equal to 2/5. This probability is not. The probability of picking a red marble second, given that you picked the red marble first, well, if you look back up at your probabilities here, that's this one right here. Picking a red marble second, given that you picked the red marble first, is 3 out of 9, which we definitely, thanks to you, wrote down here, right? Our probability of picking a red marble second, given that we picked a red marble first, is 3/9. Are those the same? Obviously not. 3 out of 9 is different than 4 out of 10. That's not the only way you could answer this, though. It's the way I like to think about answering it because to me, the words match up with the idea the best, in my opinion. But lots of people prefer to use this version. You could also have asked, is the probability of picking a red marble first times the probability of picking a red marble second, is that equal to the probability of picking a red marble first and a red marble second? Well, the probability of picking a red marble first we know is 4 out of 10. And we calculated the probability of picking a red marble second is also 4 out of 10. But the probability of picking a red marble, geez, I should not use the letter R when I'm talking about problem because I just can't help but like I start to write a P and it turns into an R. The probability of picking a red marble first and a red marble second is going to be, well, 4 out of 10 times 3 out of 9. Oh, definitely not the same. So I will point out also that if one of these things is not equal, they're all not equal, right? You can't have one equation being equal and the other one being not equal because that would show that it was independent and not independent. So they're either all equalities or all inequalities. Yes, this shows that they are dependent events. Although I feel like we usually say not independent, which definitely feels not wordier, but it's the way we usually say it. I don't know why, but it is. But it is also correct to say that they are dependent events. I think the reason we actually don't say it is because if I say the word dependent, you might feel like you might have just missed me saying the first in part of it. So we don't say dependent, we say not independent to make it really, really clear that it is not independent. Yeah, I really feel like that's why we say it that way, probably. Um, sure. Let's look at one more example. Yeah. So sure, let's look at this one. Sure. Let's see, flip a coin 3 times. We'll say that A is the first flip. Event A is the first flip. No, event A needs to be an outcome, not just the thing that's happening. So let's say that event A is the first flip is a heads. Event B is the second flip is a heads. And event C is the third flip is a heads. Are events A and C independent? Okay. Well, there's a lot of ways to answer this question. But here's what we need to think about. We need to ask the question in one of 3 ways. Either is the probability of, say, now let me ask you a question. If I was going to think about conditional probabilities, which is the one that's easier for our brains to think of? Is it easier to think of event A happening given that C happened, or event C happening given that A happened? I know what I think. Yeah, I think it's always easier to think of the probability of the later thing happening, given that the earlier thing happened. Even though it doesn't actually really matter, it's just easier to think of that as like, okay, yeah, this first thing happened first, and then what's likely that the later thing happened. So we could either try to see is the probability of C given A equal to the probability of C? Or if we prefer, we could do it as the probability of A intersect C equal to the probability of A times the probability of C. All right, well, good question. So I think in either of these cases, we probably have to write out all the things that happen. Or at least I do it first, and then maybe we don't have to after we figure out how it works. So let's write out our sample space, omega here. So if we flip a coin 3 times, how many possible outcomes are there? What's the size of my sample space? It's my favorite number. It doesn't help you. It might help you if I told you I was born on August 8th. My favorite number is 8. And the answer here is 8. There are 8 possible outcomes because we're flipping 3 coins and each coin has 2 possible outcomes, and 2 times 2 times 2, right? Heads or tails times heads or tails times heads or tails is 8. So whenever you're flipping some number of coins, the number of possible outcomes, if it's a 2-sided coin, is 2 to that number of times power. So omega has 2 to the third entries. And it's either we flipped heads, 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 or heads, heads, tails, or heads, tails, heads, or tails, heads, heads, or heads, tails, tails, or tails, heads, tails, or tails, tails, heads, or tails, tails, tails. And each of these 8 events is equally likely because, right, it's a fair coin. There's nothing weird going on here. So let's answer it this way first. What's the probability of A? Well, the probability of the first flip as an H is 1, 2, 3, 4 out of 8. Not surprising that the probability of the first coin is a head is 1/2, right? Because you flip the first coin, there's a 1/2 chance it's a head, there's a 1/2 chance it's a tail. And the probability of C that the last coin is a head is, let's see, 1, 2, 3, 4 out of 8. Just 1/2. And the probability of A and C, the first coin is a head and the third coin is a head, is 1, 2, 2 out of 8, which is 1 out of 4, which definitely is equal to 1/2 times 1/2, which is the probability of A intersect C. Sorry, that's not, I didn't mean to write that. I meant the probability of A times the probability of C. Apologies. Which shows they're independent. The probability of the intersection is equal to the probability of the first one times the probability of the second one. And that's probably the easier way to do this one. Although, if we wanted to think of it this way, we probably could. So, I probably need more paper. Yeah, sure. So again, we know the probability of C is equal to 1/2. And the probability of C given A, well, let's see. If we look at C given A, so let's look at our reduced sample space. Our omega A here is all the ones we have an H first. So it's HHH, it's HHT, it's HTH, and it's HTT. So the probability of C given A, well, C is that the last was an H, so it's this one and this one. So the probability of C given A is 2 out of 4, which is 1/2. They're the same. That means they're independent. And that makes sense, right? If we think about like flipping coins, it shouldn't matter what happened when you flip the first or the second or however many times before. This coin flip here, its probability of being heads or tails has nothing to do with however many whatever coins you flip before that, whatever they came out to be, right? Each event's independent because like they are. And it sounds like a dumb thing to say, but like they are independent because knowing what happened before doesn't affect the probability of what's happening now. This is one of the reasons why like roulette tables in Vegas show all the things that happened before. They're trying to introduce bias among the bettors so that they are say, oh, red came up 3 times. It can't be red again. It has nothing to do with what's going to happen again. Right. So if you ever do go to Vegas and are playing roulette, don't look at that. Don't look at that at all. It has nothing to do with what's going to happen. It's hard not to, though. It's really hard. Anyway, you're like, oh, yeah. All right. All right. Black 7 times. Can't be black again. Definitely going to vote black. So, doesn't matter. Nothing matters. Seems like a good stopping place. So Yeah, practice final on Canvas, fill out the survey, office hours next week. Good luck on your final. Hope it goes well. It's your last math test, possibly ever. I mean, you might have to take a stats class at some point. I don't know, but like, this could be the end of your math at UC Davis. I hope it is. Hope you all have a nice break as well. And if you do take a stats class in the future, I can be moderately helpful with statistics. So if you're looking for statistics help, I'm often the person people find first on campus. So you know where to go if you're looking for stats help. I can't promise to be super helpful because some of it's I don't use it as often as I used to, so I've forgotten a lot of it, but that doesn't mean I can't be some help. But yeah. Oh yeah. So definitely the conditional probability stuff certainly comes up. Yeah, kind of. I mean, all of this comes up in some way in stats. There's a lot of other things that we haven't covered that also come up, but like certainly, I would say I'd be surprised if you took a stats class and didn't see most of this in there at some point. Thank you. You're welcome. Thank you. Yeah, you too. Thanks. What's up?
So I am actually in stats right now. So
Okay.
as help, should I just come?
Yep.
I was thinking about coming
Yeah,
to
yeah.
help one anyways.
Yep. Find me in the calc room or wherever I am, and I will happily help you as much as I'm able to.
Okay, yeah, because like looking up now, I get it because we already
Uh-huh.
covered it and it's better. But I think in stats, I'm kind of like this is my first time taking stats. 'Cause
Sure.
I didn't take it in high school. But yeah, so I'll probably be. Thank
Okay.
you.
Yeah, you're welcome. Why can't I close the Zoom? That's why. There we go.